Okay. Hello. Good evening and welcome back to the weekly live tutorial sessions on mechanics and control of robotic manipulators. I am Isaac John, the TA for the weekly live sessions. So we are heading on to weeks 7 worth of contents for this course. And until now, we have been focusing on mechanics of robotic manipulators, which consist of uh, kinematics. We have also seen how to uh, model the dynamical equations of motion of a robotic manipulator. And now we would be moving on the basics of motion controller and what are the different kinds of motion controller that we would be dealing with uh, in case of a robotic manipulator and some of the very basic principles behind it. So for this week, we have basically covered the following topics. We've had a brief introduction to robot motion controllers, through the lectures uploaded in NPTEL. Then we have also seen various types of manipulator control and their concerns. There in case of certain implementations, there are some initial conditions that has to be enforced for the controller to work. We have seen a few examples of kinematic control. We have seen open loop and closed loop examples for kinematic control. There were a few MATLAB simulations of either of these cases of kinematic control. And finally, we have seen a few examples of, or rather, the open loop and closed loop examples for dynamic controls. So let's have a brief overview of motion control, why we need motion control, and what is it that we are expecting from motion control. So to put it simply, motion control is a subfield of automation encompassing the systems or subsystems involved. It's supposed to be involved in moving parts of machine in a controlled manner. So what it says is it's essentially an integral part of automation, which encompasses subsystems. The easiest thing that you can think about is the manipulator itself, uh, comprising of several moving parts or links connected by joints. And then we would require these rigid bodies or this multi-rigid body system to move in a controlled manner, as per a desired trajectory. And then motion controller contains the motion profiles and target positions for the application and creates the trajectory for the motor and or actuator. So depending upon your controller, it could be a set point controller. For example, if you have a start point of your manipulator arm to be at a point in the workspace, maybe if I call this to be the start point, and you simply want your manipulator to move to a goal position, depicted as goal position. In case of set point control, you would only require your manipulator to move from your initial position, something like this, to the final position, something like this. You don't really care about the path that it tracks from the start position to the goal position. Or in case of a trajectory control, or in case of a tracking control, uh, between the start and goal positions, the time history of all the intermediate points will also be specified. The time history of position, velocity, and acceleration of all the intermediate points will be specified, and the robot will be tasked to track all the intermediate points from the start point to the goal point. Right. So depending on whether the set point or set point control or trajectory control, uh, the controller would have to decide, on or the controller would have to provide the corresponding inputs to the motors or to the actuators. So that's what this point says, the second point says. And another aspect is, why do we need these motion controllers? Like until now, we have derived the kinematic and dynamic model, which is essentially a mathematical uh, representation of the manipulator system. So if we have a mathematical model, why do we need a motion controller? Couldn't we just simply use the mathematical model to find the inputs? What is the reason for having a motion controller? Well, we address the need for a motion controller in using these 3 points. The first point says robots similar to many engineering applications. Robots in many engineering applications, it's impossible or very difficult to obtain an exact dynamic model of the robot due to many unavoidable reasons. For example, we know that a dynamic model of a robot can be expressed in this very generic form. Tau would be a mass matrix multiplied by an acceleration vector plus a vector of Coriolis and centrifugal effects. And maybe if you consider the gravity, you can have a vector, basically representing the gravitational forces acting on all the links. So this basically represents a very generic dynamic model. Over here, you have a mass matrix. Over here, you have a vector of Coriolis and centrifugal effects. And over here, you have a vector of gravitational forces. So the first point says it's very difficult to obtain an exact dynamic model of a robot due to many unavoidable reasons. Maybe one reason could be, we cannot exactly estimate how this mass matrix would look like. In some cases, the mass matrix could be time varying. For example, if you take the case of a flight, as the flight goes through its path, it basically burns down the fuel. So the weight of the flight or weight of an aeroplane would be dependent on would be time dependent. And in some other cases, it should be fairly obvious that we cannot really estimate the masses. We cannot exactly estimate what could be the mass of the individual parts or the individual links. What could be the center of the position of the center of mass? The moment of inertia. We cannot exactly determine those, whatever be the case. And then there could be some cases where we cannot model some of the physical phenomena that is actually happening. For example, here we haven't modeled the effects of friction. But in any component or in any multi-body systems, there is going to be some effect due to friction. There is also some effect due to the presence of damping, hysteresis. All these effects are basically unmodeled, in this dynamic model. So that also, accounts for some sort of uncertainties in obtaining an exact dynamic model. Then the second point is, moreover, the presence of external disturbances and parameter variations are inevitable in robots. So external disturbance. For example, if a robot is actually asked to execute a trajectory carrying a specific payload, due to external disturbances, maybe it could have some unprecedented interactions or contacts in the form of as an external disturbance. Those things cannot be accommodated in real time. The external disturbances and parameter variations, as I was saying earlier, the mass, the mass of the individual link center of gravity, all these things can be, there could be variations, as time goes by. So that also accounts for variability in the dynamic model. And then good performances cannot be reached without advanced controllers. So again, due to these uncertainties and external disturbances, we cannot have a exact representation of the dynamic model of a robot. So in that regard, to compensate for all these uncertainties and parameter variations, we need to design a motion controller so that all the unmodeled dynamics and parameter variations can be taken care of, so that the robot can move in a satisfactory manner. It can track a trajectory to a very high accuracy. So let's see some of the philosophies adopted in motion control that has evolved over time. So during the mid 70s, we call those period as classical robotics, where we use exact models and we never had any sort of sensors, right? So just like what I was saying earlier, we use this exact model m of q dot q w dot plus n of q dot. We use these models as such, right, for controlling the robot. And we also assume that the model that we have derived is a is an exact representation of the actual system. So all the dynamics we try to model it as close as possible to the real system. And then to control the robot, if we have a desired trajectory specified by q of t, q dot of t, maybe q desired of t, q desired dot of t, and q desired double dot of t, where this is the desired trajectory. We can plug all these desired trajectory coordinates into the dynamic equations of motion, and from here we'll be able to obtain this torque control vector torque. That is what we would be supplying into the motors. And as a result, this is what we were using during the mid 70s. Here we were using the exact models and no sensing. And during the mid 80s, with the advancement in sensors and sensor and related technologies, we shifted to relying entirely on sensing. No models, but we rely heavily on sensing. For example, the classic PID control, which can be written as probably the control vector would be, a proportional gain multiplied by difference between the desired and actual positions. Then KD, a derivative gain multiplied by the derivative of proposed the desired velocities and actual velocities, and KI, this integral gain multiplied by the integral of the error, the desired trajectory and actual trajectory. So this is actually basically a very simple PID control, where we multiply a proportional gain with the difference in the actual position, and then derivative gain multiplied by the rate of change of error, and an integral gain multiplied by the integral of the error between the positions. This would account for the steady state error. This would account for the error, the true error, and this would basically anticipate. If the error is increasing high, the derivative gain would increase, and if the error is decreasing very fast, the derivative gain would also, kick in to anticipate the further the future changes in the error. So here, as you can see, we are purely relying on feedback, right? Desired would be a feed forward term. This is what we expect, and the actual position, the actual velocities, and actual positions in this term, integral terms, we would get these actual coordinates of positions and velocities from the sensor feedback. So that's why we are relying purely on sensors. And as you can see, there is no model-based terms. There is no terms based on the model's mass, its inertia, or center of gravity. No such terms are there. We are purely relying on the sensor feedback. That is what this reactive paradigm is about. And then from the mid 90 onwards, we would be using this model based at higher levels and reactive at lower levels. Maybe at the manipulator level, we would be using the model based control. And at the lower levels, maybe at the sensors, we would be using this using the reactive scheme, which is purely based on sensor feedback. And then from mid 90 onwards, with the advent of computational access to more computational power, we would be using probabilistic approach, where we would be integrating models and sensing. So we would know that it's if you are relying on sensors, there is a lot of uncertainties associated with the sensor data, and whatever data we gather from the sensor, there is always some error associated with the sensor, and with the which we cannot really know. We cannot really have a deterministic knowledge about the error, but the error distribution will always follow a Gaussian curve. So we can model this error as a distribution and thus accommodate those errors while we are accommodating the sensor errors. So seamless integration of models and sensing, inaccuracies in modeling and inaccuracies in sensing, we can also take that into account. So later we would start using sensor fusion. We would be measuring the same information using multiple sensors, and then we would fuse the information from multiple sensors for a better estimate of the trajectory, or the better estimate of the quantity that we are trying to measure, or using the probabilistic approach. And then later, from 2015 onwards, we will be using data-driven controls, using deep and reinforcement learning. So essentially, we would train the robot using, using the actuator forces and the position that is reached by the robot for the corresponding actuator inputs. We would create a dataset for training a model, and using that model, we would be able to predict, for any combination of the actuator inputs, what would be the output that we would be getting from the end effector. But then that would also require training the system using a lot of input-output data. That is what we have to, which is what we would be generating on our, as an offline procedure. That's about the control paradigm that we have seen, over the years. Then let's see what are the steps in control design. The first one would be, familiarization with the physical system under consideration. So the first thing for motion controller is to model the system as accurately as possible to the real system that we are studying with. So we all know that the dynamic model can be represented in a very generic form as tau would be m of q multiplied by q double dot plus n of q dot. So the familiarization with the physical system under consideration would involve estimating the masses of individual links, their moment of inertia, the location of their center of gravity, the link lengths, all these aspects. Then, our ability to model it as accurate as possible to the real system, right? So if a real system has a lot of effects due to friction and damping, the model that I have written here would not be accommodating those. We can only use this model if the friction and damping in the model is very negligible, that it does not really have much of an effect on the control forces. So in that case, this model is valid, but for all the other cases, we will have to, refine our models. So the first step in control design is to have a very good understanding of the underlying robotic system and then to model it mathematically, which is the second step, the modeling of the underlying manipulator. And then we would also need to specify, what do we expect from a motion controller, right? How fast should the controller should it react? What should be the steady state error? All these things comes under controller specification. For example, if we have if our desired output is a steady output, maybe if we have a single link robot manipulator and this is our desired theta output, depending upon our controller specification, our actual output would look something like this. It would start from a zero position or some other position, and then it would gradually converge to the desired output position. So how fast, our actual position should converge, and should it gradually converge? Should it converge very fast, something like this? Or is it allowed to have some oscillations? And how fast the oscillation should damp out? What should be the steady state error? All these questions or all these requirements are to be satisfied by the control specification. And while we are designing a motion controller, it should be as per the control specification. Depending upon how fast or how much should the what should be the steady state error, how fast should it converge, what should be the how fast should be the disturbance should be damped out. All these things will be taken care of by the control specification. And another aspect is the control objectives, which are stability, regulation, trajectory tracking, and optimization. So the most important control objective would be the stability of the controller. So, for example, if we are not bounding our control inputs, maybe if due to some reason, if the control input is actually going out of bounds, the system will become unstable. As the control output grows, the system will start making very large motions, and after a while, it probably won't be able to. We won't be able to stabilize it. So. The first and foremost objective is to ensure that the controller is stable. And the second step is basically a regulation, which if we have a start position of the robot send effector and we have a goal position. So depending upon your control output, the manipulator should move from the start position and go to the goal position. Which is basically what this regulation says, in a very controlled, stable manner. And in case of a trajectory tracking, apart from the start and goal positions, the time history of all the positions, velocities for the intermediate path will also be specified. And the controller should closely follow, the positions and velocities according to the desired trajectory. So apart from the start and goal position, it should accurately follow the time history of the desired position and velocity. And the final part would be the optimization of the control parameters. For example, if you have a PID controller, you essentially have three controller gains, KP, KD, and KI. So depending upon your control specification, you have to find out the optimal gains for KP, KD, and KI, which will be fully dependent on the control specification. So that is also one more core control objective or core objective in design of motion control. But the most important aspect would be the stability. We have to ensure that the designed motion controller is always stable. And then we would now see some classification of robot motion controllers. The first one would be a model-based controller, which is a motion-based controller, which is free from any of the mathematical models that we have seen thus far. So in motion-based control, they rely on pure feedback from the sensors. right? So depending upon the error between the sensor, the actual output coming from the sensor and the desired output, we would be giving the control input to the actuators. So, for example, one example I could give you is the PID control. So these rely purely on sensor feedback. There is no model. Uh, uh, Mathematical models are not coming into picture, and their main feature is they are easy to use because a PID control can be universally implemented in any robotic system. We don't really need to know how the system behaves because we don't have a mathematical model, but purely based on their output from the sensors, we can do some control action. So they are easy to use, but they are sluggish and produce poor tracking performance. So since it's reactive, since it can only react based on the current error, it's basically sluggish. It takes a lot of time to correct the errors or to accommodate for any unwanted uncertainties. But if you have a model-based control, you basically have a virtual mathematical model of a robotic system. So they are very comparatively efficient and simple because we already know how to model a robotic system, using the Euler-Lagrange equations of motion or Newton-Raphson motion. So the key aspect is we should know, we should have an estimate of accurate estimate of the mathematical method. So one example I can give you is that if you have a robotic manipulator, something like this, probably something like this, you can maybe probably consider that it has a lot of inertia to move along this axis, x-axis, but or maybe I'll give probably a better example. Maybe you can have a 3D of robot manipulator, something like this, which can rotate about a vertical axis, and then 2 degrees of freedom, uh, a 2 revolute joint, something like this. These are perpendicular to the plane of the board, something like this. Right. So this is like a 3D of robot manipulator. So you can say that when the robot is fully stretched, something like this, the rotational inertia about the robot about this vertical axis is going to be very high, right? If it is fully stretched, the moment of inertia would be proportional to the length of this fully extended part. So the rotational inertia about this vertical axis is going to be very high. But if the arm is folded, something like this, since the center of mass is concentrated near this axis, the rotational inertia would be very low, right? So in that case, from the mathematical model itself, we'll be able to know if the inertia is high or if the inertia is low. So if the inertia is low, we are only required to give a smaller control input, to rotate about this vertical axis. And if it is fully stretched out, we would require a higher force or a higher torque about this vertical axis to achieve a same rate of rotation because it's fully stretched out. And as a result, the inertia is also very high. So we'll be able to obtain all these information from the mass matrix, just from the mass matrix alone. So if the control input has components of this mass matrix, we can anticipate, whether the control input is high or whether the control input is low. But if you are using a pure model-free or a pure motion-based controller, we cannot anticipate it, right? We don't have any information from the model. So as a result, we give a control input based on the feedback. So, if the model is fully stretched out, it will take some time for the error to grow, and as a result, the control input, the necessary correcting control input would also take a lot of time for it to catch up. The same goes for when the robot arm is fully folded, right? Due to lower inertia, initially the robot arm would be moving faster than what we actually desire. So we would have to wait for the error to grow to perform the corrective action. So that's why it's a pure motion based would be sluggish. But due to the presence of these terms in the model based controller, we can always anticipate, the correct amount of control inputs. Okay, so that's about the difference between model-free control and model-based control. Both have its own advantages and disadvantages. And then another classification regarding the motion control is when the model or the constant parameters are not accurately known. So, for example, as I was saying earlier, we tried to estimate or we tried to derive the governing equations of motion using this formula m of q double dot plus n of q dot. For any robotic system, we try to derive equation of motion of this form, but it may not be possible to estimate the constant physical parameters as accurately as possible, right? If you have an actual robotic system, we cannot exactly measure its center of gravity. We cannot exactly measure its the position of the center of mass. We cannot exactly determine its inertia metrics. It's not always going to be possible to exactly measure all these constant parameters. So what to do? If we cannot exactly measure these parameters, what to do? So one philosophy of control called robust control aims at controlling with a small error a class of robotic manipulators in which the model is not accurately known with the same controller. So if the constant parameters are not known, but if we know that the errors are within a bound, if we know the upper and lower limit of a bound, the robust controller can still control the robot manipulator, be it a set point control or be it a trajectory control, uh, even if the constant parameters are not known, despite having some small errors, in the estimating the constant parameters. Whereas in case of this adaptive control, it deals with the uncertainty in the system parameters or unknown constant parameters, and it requires the precise knowledge of the structure of the system. In a lot of cases, we may not be exactly know the system parameters. Sometimes the system parameters could also change with time. Like as I was saying earlier, in case of an airplane, the mass of the airplane is not going to be constant, right? As the fuel burns, the mass of the airplane could be decreasing. And maybe as time goes by, the effects due to friction could be no longer negligible, right? So in this equation of motion, we don't have any term to accommodate for friction in terms of friction in the joints. So, but eventually, as the robot completes a lot of operating cycles or operating cycles, friction could also come into effect, right? So again, we cannot exactly know what would be the coefficient of friction or what would be the coefficient of damping. So even with those uncertainties, the uncertainties in the system's parameters, the controller should still, account for those uncertainties and still should deliver a satisfactory performance as per the controller specification. So that aspect would be under this adaptive control. But again, these are only just for just for the sake of classification, we won't be discussing much about robust control or adaptive control in detail in this course. Uh, Now let's have a more relevant classification of robot controllers. So the first important classification is kinematic control, where only the kinematic models are used. So this could be relevant in case if a robot is actually moving very slow. We don't really need to consider the dynamic effects, due to inertia or due to the motion. Inertial effects could be very slow. So we can adopt a very simple kinematic control when the robot is actually moving in a very slow space or in a quasi-static manner. But if the inertial effects are not negligible, if very high, if a very fast trajectory tracking is of our interest, we would have to go for this dynamic control, where the robot dynamic model is also accommodated in designing the motion controllers. And then one another philosophy that we will be discussing in detail in the next week is called a cascaded or a dual loop control, where we would be using a kinematic control as an outer loop, and whatever we obtain from this outer loop, we will be feeding into an inner loop, which deals with the dynamic equations of motion. So for the remainder of these two lectures, we'll be covering the various kinds of kinematic and dynamic control. And for the next lecture, we will be discussing about this cascaded control. So within the kinematic control, we have examples for open loop schemes and closed loop schemes. For kinematic as well as dynamic controls. So in the upcoming slides, we will be seeing the various examples for open loop and closed loop control schemes for both kinematic and dynamic controls. Okay, so and within either of these cases, within kinematic and dynamic controls, we have even more even more further classification or further ways to classify the motion controllers or any controller. It may not be strictly limited to motion controller. So design of classification of controllers based on interest or application. The first one is motion or position control, which is what we would be dealing in this course. Another one is basically the force control, where we would also be controlling the forces acting at the end effector. Maybe if you want to grasp, if the end effector has to grasp something with a specified amount of force, we would be using force control, and then a hybrid control, which is essentially a combination of both force and position control. And then impedance control. If the robot has to interact with the environment, the change in impedance, due to the interaction with the external environment, due to contact with the foreign bodies or with contact with human beings, those sort of aspects comes under this impedance control. Especially for interactive applications. And then another one would be classification based on the space considered. Whether we want a control over joint space, whether we want a control over task space, or whether we want a control in actuator or in sensor space. Yeah. So those are various aspects of classification. And then another classification would be based on nature or reference inputs. So the first one, we have already seen this. The first one is called set point controllers, where, if you have an RR manipulator, something like this, The initial location would be somewhere around here. I'll call this the initial position. And the final position could be somewhere around, something like this. Something like this. So this could be the final position. So in set point control, we are only worried about achieving the final position from the initial position, and we don't really worry about the time history of all the intermediate points. So you have an initial configuration specified by q at time t equal to 0, and then we have a final position q maybe desired at t equals tf, but all the other intermediate points are not really important. So we'll have the q desired, maybe q dot and q double dot can be considered to be 0. So we are only worried about converging from an initial position to the final position without any worry about all the intermediate points. Whereas in the case of a tracking controller, apart from the initial and final position, we would also want the robot to track a trajectory specified by the time history of position, q desired of time and q desired dot of time. So all the intermediate points will also have to be tracked as accurately as possible. So for example, if this is the track, this is the track that we have to track. All right, this is the trajectory that we have to track. So at time t equal to 0, this would be your start position, and this should be the time t equal to tf, should be the goal position. But then more often, you will find your initial position of your robot at time t equal to 0. This could be your actual position of your robot, q actual. So as the time evolves, maybe if you consider this to be the time axis, as the time evolves, your robot's trajectory should converge to the desired trajectory. So if I label this as the desired trajectory, in tracking controls, as the time evolves, your the robot's end effector should gradually converge to the desired trajectory, and finally it should end at the final position. Right? If the initial position and the actual position are coinciding, it can track. But if the actual position of the robot at time t equal to 0 is different from the initial desired position, it has to gradually converge to the desired trajectory. And how fast it can converge, that all depends upon the control parameters. So that's the main difference between set point control and tracking control. All right. So now we would move on to the design of kinematic control. So as I was saying earlier, within the kinematic control, we have open loop and closed loop control schemes. So the first one that we are considering here is an open loop scheme. An open loop scheme, and we call the scheme as inverse differential kinematic control. Right? I'll explain why we are calling it as inverse differential kinematic control. So let's see what are the objectives, or what is it that we are expecting from this kinematic control. So we would be specifying or we would be having a desired trajectory of the robot specified by the desired joint positions and desired joint velocities, or desired end effector positions and desired end effector velocities. So, for example, if I have a 2R robot, something like this, it's a very simple example to consider. So, I have a 2R robot over here, and this could be the end effector. And I want the robot to track a trajectory, something like this. So this would be at time t equal to 0, and this would be at time t equal to tf. So the initial position, I would specify the initial positions and initial velocities in Cartesian space, because that is more convenient for me. Because we can visualize, how the initial position and velocities would look like in Cartesian coordinates. So initial position and velocities, I will depict it using, x and y at time t equal to 0 and at time t equal to 0. And then maybe initial velocities, x dot at time t equal to 0 and y dot at time t equal to 0. So collectively, I can call this x and y as eta. And, eta is nothing but the vector of Cartesian coordinates x and y. And the velocities, I can call this as eta dot, where eta dot would be x dot and y dot. We can recall from the kinematic model, from kinematic model, we know that eta dot is j of q multiplied by q dot. Fairly straightforward kinematic model, right? And then we would be specifying this trajectory, right? The time history of positions and velocities in Cartesian coordinates. So we will be having eta desired of time and eta desired dot of time. So these two trajectory coordinates, the positions and velocities, would completely specify the trajectory that we want our robot to track. Right? So the given parameters are, I've used mu here. So mu and eta are basically the same. So I've used it interchangeably. So if the desired trajectory is specified in terms of eta desired dot, the control input that we would be supplying into the motors are the velocities of this joint, maybe q1 dot and q2 dot. So from this kinematic model, if I substitute eta desired dot into this equation, you will get eta desired dot would be j of q multiplied by q dot. And thus your control input q dot would be j of q inverse eta desired dot. Right? Now you got the control input. Now you essentially got the control input, control velocity input that you should be supplying into the motors. So if you supply this control input into the motors, the robot would basically execute this desired trajectory. So that's what this equation essentially says, right? If you want the robot to execute a desired trajectory, you multiply that with the Jacobian matrix. We can always assemble the Jacobian matrix because it's based on the geometry of the robotic manipulator. And Q dot would be the control input. In kinematic control, Q dot would be the control input. That is what we would be supplying into the motors. So, and there are some conditions for which the control input would work, right? So if you look at this control equation, Q dot as J of Q inverse theta desired dot, this control scheme would only work if eta desired dot is not 0, right? Because if the velocity is zero, this whole term is going to be zero, and as a result, q dot is always going to be zero. So the first and most important condition is mu dot should not be equal to zero, right? Otherwise, the control input is always going to be zero. So mu dot should always be non-zero. And other important condition that you have to be aware of is for this control to work, the initial position uh, of the trajectory should coincide with the actual initial position of the robot, right? Because if the robot is in some arbitrary initial position, maybe somewhere around here, right? And if the initial position of the desired trajectory is not coinciding with the initial position of the actual robotic arm, if you try to implement this control scheme, what will happen is it will try to trace a path that is parallel to the desired path, something like this. It will try to trace an S curve, but there is always going to be an offset between the desired path and the actual path. So in order to eliminate this finite offset, the initial position of the actual robotic arm should coincide with the initial position of the trajectory. So if both of these points coincide, then the robot will try to track through the desired trajectory. But if the initial positions are not coinciding, there is always going to be an offset between the desired and the actual path. So the condition would be, mu of desired at time t equal to zero. So this is this term is the initial position or initial configuration of the desired trajectory, and this term over here, mu at t equal to zero is the initial position of the actual trajectory. So both will have to coincide for this controller to work. So you should also remember this is an open loop scheme. There is no feedback term in this control. In this control law, there is no feedback term. And the first important condition for this controller to work is mu desired dot should not be zero. Because if that term is zero, this control input will always going to be zero. And the initial position of the desired trajectory, mu desired at t equal to zero, should be equal to the initial position of the actual trajectory. Then only this scheme would work. All right, I hope that is clear. Yeah, now let's move on to the closed loop scheme. So here as well, you essentially specify your desired trajectory in terms of probably in terms of the Cartesian space, maybe mu desired of t and mu desired dot of t, right? But here we are dealing in a closed loop manner. We are taking feedbacks into account. So these are the trajectory in task space. But now you have an additional constraint, right? The objectives of this controller are the system should be asymptotically stable, right? As time t10 goes from 10 to infinity, the difference between the actual joint position, I'll denote it as q, where this q would be the actual joint position, So as time t tends to infinity, the actual joint position to converge to the desired joint position. I'll label this as desired desired joint position. Right. So as time tend to infinity, your actual joint position to should converge to the desired joint position. Or in another way, at time t tend to infinity, q tilde should tend to 0, where q tilde is the difference between q desired of t and q actual of t. Right? The error between the actual and the desired and the actual trajectory, the actual position should tend to 0 as time tend to infinity. Right? So if I plot a graph, something like this, so on this axis, you have your time, and on the vertical axis, you have your q tilde of t, which is the error. So initially, there could be a big difference between the actual and desired. But our objective or our requirement is the controller should force this error asymptotically to 0 as time tend to infinity. Right? Or in another words, we want our system to behave as per this first order, dynamics. Q of tilde t should be should behave as per e raised to minus lambda, e raised to minus lambda t. Right? So what will happen is as t tend to infinity, this term would tend to 0, and thus q tilde of lambda t would also tend to 0. Right? So if we want the system to behave as per this equation, we want the system to follow this first order error dynamics, right? So that will be something like q dot uh, q dot of t should be equal to q desired dot of t plus lambda multiplied by uh, q tilde. Or in another words, you can write this ordinary first order differential equation as follows: q tilde dot plus lambda q tilde should be equal to 0. Right? So if you write the homogeneous equation of this differential equation, it would look something like an arbitrary constant c1 e raised to minus lambda t. This is how the homogeneous equation for this differential equation would look like. And as you can see, as time tend to infinity, this response, right, q of tilde t would tend to 0 as time tend to infinity. So the governing equation is this: q tilde dot plus lambda q tilde should be 0. So then, if we want our system to follow this error dynamics, right? What should be our control input? This should be our control input, right? Q dot should be q desired dot plus lambda q tilde. So this term q desired dot, we call this as a feed forward term. And this term q tilde, we call this as a feedback term. Right? Where this q tilde is nothing but the difference between the desired position and the actual position. And we obtain this actual position from a sensor feedback. So that's why we call this term as a feedback. Right? So the control input would be essentially a sum of a feed forward term, which is the desired velocity, added with the feedback term, which is nothing but the difference between a proportional gain multiplied by the difference between the desired position and the actual position. So, in terms of closed loop kinematic control, this is how our control input would look like. Q dot would be Q desired dot plus lambda multiplied by Q tilde dot. Now we move on to the cases of dynamic control, which again, as we were seeing, we have two schemes. One would be the open loop scheme, and the other would be a closed loop scheme. So here we consider an open loop scheme. We call an open loop scheme. And the open loop dynamic scheme is actually called inverse dynamics control scheme. So let's see why it is called inverse dynamics. So as before, the desired quantities are a desired position. We want our robot to track a trajectory specified by the desired position, desired velocities, and desired joint accelerations. Okay? So the desired trajectory is specified by Q desired of t, Q desired dot of t, and Q desired double dot of t. And then, from what we have learned earlier, we have these terms available. We know how to derive this mass matrix, and we also know how to derive this vector of Coriolis and centrifugal effects. So we also know from dynamics, we know how to derive this mass matrix M of Q and the vector of Coriolis and centrifugal effects. The governing equations of motion of a robotic manipulator is given by tau as M of Q, Q double dot plus N of Q, Q dot. Right? We basically know this we can derive this from Newton-Euler method or from Euler-Lagrange method. We have seen this in the previous lectures. So now, in dynamic sense, the control input would be the torque, or the torque we would be supplying to the actuators. So in that case, if we know the desired trajectory, and what we want to know is what should be the control input that we should be supplying into the motors. So to find out the control input, what we have to do is we simply plug all these desired trajectory coordinates into this equation, right? Into the governing equation. So the control input tau C would look something like M of Q desired multiplied by Q desired double dot plus N of Q desired dot. We are simply plugging the desired trajectory into the dynamic equations of motion. So again, this is also an open loop scheme. You can actually see there is no feedback term. There is no term coming from the sensors. So in that regard, this the inverse dynamics scheme is a purely open loop scheme, right? So for a given trajectory, we are trying to find out the torque, and this process is nothing but inverse dynamics. From what we have seen earlier. So in that regard, how does this, just like what we have seen in the case of the forward, just like what we have seen in the previous case, for an open loop kinematic scheme, there are some conditions for which the inverse dynamics control scheme would not work. So let's see what are the situations where this control scheme would not work. So the first thing is q desired double dot of t should not be 0 at any point, right? So if q desired double dot of t is 0, this term would basically vanish, right? So this term would essentially vanish and you will only end up with this term. Uh, yeah, so this is one of the first important requirement for this inverse dynamic control scheme to work, which is q desired double dot of t should not be 0, otherwise this term will vanish. And the other requirement is the actual position of the robot and the actual velocity of the robot at the very initial part should coincide with the uh, initial position and initial velocity of the desired trajectory. So, for example, I'll depict this red colored line as the desired trajectory. This should be the desired trajectory. And I'll specify this point as using the position and velocity coordinates. Eta desired, or maybe if you want to specify in joint space, that's still fine. Q desired at t equal to 0 and Q desired dot at t equal to 0. So if your robot's actual position is somewhere else, right, at time t equal to 0, if you supply this control input, your robot is going to execute the same kind of motion as per the same kind of motion, similar to the desired trajectory, but there is always going to be an offset, between the desired and the actual trajectory, right? The motion, the similarity is still there. The motion executed is still very similar, but there is always going to be an offset. So to avoid that, you have to ensure that the start position of the robot coincides with the start position of the desired trajectory. So you have to bring your the actual start position to be coinciding with the start position of the initial trajectory. Now, if that condition is maintained, your robot will track the desired trajectory if there is no disturbances. So the two conditions to be maintained are q desired double dot should not be 0. Initial position of the desired trajectory should match with the initial position of the actual robotic system. Initial velocity of the desired trajectory should coincide with the initial velocity of the actual robot. So those are the conditions to be enforced in order for this open loop dynamic scheme to work, or this inverse dynamics control scheme to work. All right, now we move on to the closed loop control scheme for the in dynamics. So as before, we have the desired trajectory specified by the desired joint positions, desired joint velocities, and desired joint accelerations. We have the actual joint positions, from the sensors, right? Apart from the desired position, we have the actual position available from the position sensors. We have actual joint velocities, from the velocity sensors. We have the inertia metrics and we have the vector of Coriolis and centrifugal effects. Now, how do we find out the control input torque? So here as well, our objective is we want asymptotic stability, right? So as time tend to infinity, we want our, uh, you know, the error in position to tend to 0, and the error in velocity is also tending to 0. The q tilde is q desired minus q, and q tilde dot is q desired dot minus q dot, right? So as time t tend to infinity, the error in position and velocity should tend to 0. So what we are trying to do is we are trying to force our system to behave as per this second order differential equation, right? Something like d square plus lambda 1d plus lambda 2 multiplied by q tilde, this should be equal to 0, right? So we want our system to behave as per this second order differential equation, right? So what would be the characteristic equation, or what would be the the homogeneous solution of a differential equation of this form? You would know that q tilde would take a general solution of the form c1 e raised to st plus c2 e raised to s1t plus c2 e raised to s2t. This is a general form any ordinary differential equation would look like. And what are these s1 and s2? S1 and s2 are nothing but minus, from this equation, or from this differential equation, you essentially find out the roots, where s1 would be minus lambda 1 plus or minus root of lambda 1 square minus 4 lambda 1 lambda 2. This would be your s1 and s2. So for this s1 and s2 to be negative, lambda 1 and lambda 2 has to be positive. Lambda 1 and lambda 1 has to be positive. So in that case, if s1 and s2 become negative, as you can see, as time tend to infinity, this term would tend to 0, right? So the consequences of having lambda 1 and lambda 2 greater than 0 is the general form of this differential equation would tend to 0 as time tend to infinity. So essentially, we want our system to follow this second order error dynamics. I'll just note it down here. We want the system, the robotic system, to follow this second order error dynamics. So if I rearrange this equation as follows, right? I am simply substituting in place of this q tilde double dot, I am simply substituting q tilde double dot as q desired double dot minus q double dot, where this term is the desired acceleration and this term would be the actual acceleration, right? But from the governing equation from the dynamical governing equation of the robot, we know this is how the robot would behave, as per this equation of motion. And from here, you can find out the actual behavior of the robot, the actual velocity of the robot. That will be, simply by rearranging this equation, you will get q double dot as m of q inverse tau minus n of q dot. So if you substitute this q double dot into this equation and solve for this control input tau, you would get this final equation like so. So this would be your control input for your this would be the control input for the closed loop dynamic motion control. Where here this Q desired double dot would be the feed forward term, and these two terms are the feedback terms. Because they are both of these terms considered this Q tilde dot and Q tilde, which is essentially the difference between the desired and actual velocities, and this would be the difference between the desired and actual positions. So the actual velocities and positions are obtained by the sensors, which is essentially fed back into the controller. So that's why we call these two terms as feedback terms. Right. So this would be the closed loop dynamic motion control, and this would be this should be your control input for the dynamic motion control. All right. So with that much recall, let's solve some sample problems on this topic. So the first question basically says it's a true or false question. It is easy to obtain an exact dynamic model of a robotic system. Would that be true or false? Exact. The keyword is exact dynamic model of robotic system. Can we really obtain an exact dynamic model of a robotic system? In every situation, would that be a true or a false? Any answers?
False.
That's false, right? Because our inability to obtain this exact dynamic model is why it is worth investing in a motion controller, because there are plenty of unmodeled physical phenomena, right? So something as simple as this one, tau would be m of q double dot plus n of q dot. This is a very idealized model, what we have seen through this course. But then there could be effect due to friction, due to damping, viscous damping or Coulomb damping. There could be effect due to backlash. There could be effect due to hysteresis, due to flexibility. All these things cannot really be accounted, in an exact manner. Right. So an exact dynamic model is a hypothetical situation. We cannot really, represent it in a virtual sense. So the statement that we can easily obtain an exact dynamic model for robotic system is actually false due to the above mentioned reasons. So the answer is indeed false. Now for question 2, if Q D and Q desired dot are the desired joint positions and velocities, then the computed velocity or the kinematic control can be given, the kinematic control law can be defined as, out of which of the following option would fit. Also identify the feed forward term in the control law. So any answer for this question? We have just recalled what is this computed velocity control is. This is essentially a closed loop law, closed loop kinematic control scheme, right? Where our objective would be, as time tend to infinity, the error q tilde of t should tend to 0. Or, q desire minus, where q tilde is nothing but q desire of t minus q uh, of t. So this would be your actual position, and this would be your desired position, and this would be your actual position. The difference between these two terms, the desired and actual, should tend to 0. So in order to realize this, in order for q tilde of t tend to 0 as time t tend to infinity, we want our system to behave as per the first order error equation. Q tilde dot plus lambda q tilde equal to 0. Right? In order for q tilde of t to tend to 0, we want our system to behave as per this first order error dynamics. Right? Because this is a first order differential equation, and any first order differential equation can be expressed in the general form. Q tilde of t would be C1 e raised to S1t, right? Where C1 is an arbitrary constant and S1 is a constant dependent on the system. So, the homogeneous solution for this system can be solved by solving this algebraic equation. How would it look like? D plus lambda q tilde, this should be equal to 0. And D would be minus lambda. Right? So your S1 would be minus lambda. So your system would look something like this. Your system behavior would look something like this. Q of q tilde of t would be C1 e raised to minus lambda t. So if your system behave as per this error dynamics, it is guaranteed that as time t tend to infinity, this term would asymptotically tend to 0. Right? So if asymptotic stability is desired, you have to force your system to behave as per this error dynamics. Right? So q tilde dot plus lambda q tilde should be equal to 0. This is how we want the system to behave. And if I substitute in place of this q tilde dot, q desired dot minus q dot plus lambda q tilde as 0. Now your control input q dot. So the control input q dot would be now q desired dot plus lambda q tilde. This would be your control, right? And you can also rewrite this in the following way. Q dot would be q desired dot plus lambda multiplied by, in place of q tilde, I'll write it as q desired minus q actual. Right? And as we have said earlier, this term is basically the feedback term. Because it has this term q, which is the actual position obtained from the sensors. And this remaining term, this one, q desired dot, this is what we call the feed forward. Feed forward. We are simply feeding that into the controller, but this term, q actual, this comes from the sensor, and through a feedback loop, this is actually fed into the controller. So from this, what would be the answer? I think the answer should be option A. Sorry, I think it should be C, right? Q desired should be Q desired dot plus lambda multiplied by Q desired minus Q. And the feed forward term is this one, Q desired dot. So yeah, that will be the answer for question 2, option C. Let me know if there is any doubt. I can clarify that if any doubts or if any concerns are there. Now, moving on to question 3. It says the expression for a proportional integral controller with a feed forward term is. So as we have seen here, there is no term that has attributes from the mathematical model. So in that regard, you can call this as a model free control, because there is no Jacobian matrix, there is no mass matrix. All these things are not here. Or in other words, you can also call this a motion-based controller. And this one relies purely on sensor feedback. Right? This control scheme relies purely on sensor feedback. So again, this is a fairly straightforward question. We know the proportional controller is Kp multiplied by Qd minus Q. Is proportional to the error between the position, then multiplied by the an integral gain to the integral of the error, Q dz minus Q multiplied by dt. Then we also have to add a feed forward term, Q desired dot. Just like we have seen in the earlier case, Q desired dot will come as a feed forward term, but the other two terms, due to the fact that it has this actual position here coming from the sensors, these two terms becomes the feedback term. So here, in case of question 3, the answer is still option A. Right? Proportional controller, you have a proportional gain multiplied with the error itself and integral gain multiplied by the integral of the error, where error is nothing but the difference between the desired and the actual positions. So here as well, the correct option is option A for question 3. And now we move on to question 4. So finding the time history of position, velocity, and acceleration for a set of input torque is called forward kinematics, forward differential kinematics. This is a fairly straightforward question, right? We have discussed this a few weeks ago. This is not really a control-based question, right? You have the governing equation of motion as tau would be m of q, q double dot plus n of q, q dot. So it says the position given position, time history of position, velocity, and acceleration. So it's obviously going to be a dynamic problem, right? Because you are asked to find out the input joint torques. Find input joint torques. So it's a dynamic problem. So we can essentially eliminate all the kinematics from the options. So the only question that remains is whether it is a forward dynamic problem or an inverse dynamic problem. Here it is specified that Q, Q dot, and Q double dot are all given. We are trying to find out this vector tau.
Dynamics.
Inverse. Is that your answer? I couldn't hear that properly.
Inverse dynamics.
Yeah, okay, inverse. That is indeed true. Because this is an act of controlling the robot manipulator. If you know the trajectory in terms of position, velocity, and acceleration, what should be the control inputs of the motor so that the desired trajectory can be realized. That is essentially the definition of inverse dynamics. And forward dynamics, it's like simulating the robot, right? If you give the control inputs to the motor, what will be the trajectory of the robot? So it's an act of simulating. You apply some input and observe what will be the reaction of the of the manipulator. So that is forward dynamics. But here, if the trajectory is given, finding out the control input is essentially the inverse dynamics problem. Yeah, I believe we have a wrong answer. The option should be inverse dynamics, not forward dynamics. Uh, Sorry, I think I probably might have confused. Okay. So the question says finding the time history, not given the time history of position. I think I may have confused myself and probably participants. Uh, I have wrongly interpreted the question. So instead of given, it's actually finding the time history of position, velocity, and acceleration given the input torque. Uh, Instead of finding, it should be given input torque. So again, from what we have discussed, the logic is correct. So the question actually asked the opposite thing to what we have discussed earlier. So in that regard, the correct answer should be forward dynamics, right? You are supplying some control torque into the manipulator, and you are trying to find out the time history of position, velocity, and acceleration. So it's very similar to simulating the robot in a virtual environment, right? You supply some inputs and see how the robot reacts, right? So that is the process of forward dynamics. Finding the time history of position, velocity, and acceleration for a given set of input torques is essentially a forward dynamics problem. So I'm sorry if I've confused. Again, if there is any confusion, please let me know. I can, revisit this question.
Differential, sir.
Sorry? Yeah.
Differential.
It's not differential, it's forward dynamics. Differential is always in the velocity level, right? Forward differential kinematics and inverse differential kinematics, it does not deal with the forces. But here in the question, we are dealing with the torques as well, input joint torques also. So because of the involvement of torques, that instantly becomes a dynamic problem. Now, the only process now is to identify whether it is a forward dynamic or an inverse dynamic problem, right? Because of the involvement of joint torques, all the kinematics can be immediately be ruled out. Okay. So now, regarding question 5, a basic outline of control system is depicted in the following figure. Identify the correct components from the following. So, this is a very basic outline of a control system. But you are supposed to find out what these components are, or what these items basically are. So I'll just give a brief overview of how a control system would look like. You have a robotic manipulator or we can call them collectively as a plant or a plant that we are trying to operate. So an example would be a robotic manipulator. Over here. And this robotic manipulator would be controlled by a controller from here, controller. Okay. So depending upon the controller we design, it will give an input to the manipulator, maybe in terms of this control torque vector tau c. If you're dealing with a dynamic control, then if a controller gives a control input to the manipulator, it reacts. And the reaction can be measured in terms of the actual position, q, actual velocity, and actual acceleration, q dot and q double dot of e. And with some sensors, the actual position, velocities, and accelerations can be measured. So here we have this q dot, q actual, q dot actual, and q double dot actual. And what we would do is we would compare this actual with a desired trajectory coordinates, maybe q desired dot, and q desired double dot. And the difference between the actual and difference between the actual and the desired trajectory, we would give this difference, maybe q tilde dot, and q tilde double dot into the controller. And inside the controller, maybe we can have a control scheme, whatever we have seen earlier. Something like m of q multiplied by q desired double dot plus. You can sit there. Q desired. You can sit down, take me class. You can have a control law, depending upon your preference inside this controller, something like m of q multiplied by q desired double dot plus lambda q desired tilde minus q tilde dot plus lambda. This is lambda 1, this is lambda 2, q desired minus q actual, something like this. And based on this control law, it would give a control vector. So it keeps on going and going and ongoing. So based on this generic outline, can you find out can you basically fill in, or can you identify what are these components, A, B, C, D, and E? So out of these options, we have plan, then you have a controller, then you have a sensor, then you have a feedback signal, then you have an error signal. So what does this one look like? Option A. So if you compare this A with this diagram over here, A basically points to controller, right? A is analogous. This part stands in for controller. So A is basically the controller. And B would be the plant or your manipulator. And C would be your sensor. If you compare that with this would be your sensor. And whatever you obtain from the sensor is nothing but the feedback signal, the actual coordinates of position, velocity, and acceleration. So D would be your feedback signal. And whatever you obtain from here, after comparing the input reference and the actual signal, this would be your error. That is analogous to this tilde terms, q tilde dot, and q tilde double dot. So E would be your error signal. So in that regard, I suppose the correct answer would be controller plant, sensor, feedback signal, and error signal. Option C. This should be the answer. Option C. So I hope that is clear. So if there are any doubts regarding this, please let me know. I can clarify that. And yeah, moving on to question 6. State whether the following statement justify the need of a robotic system. There are two statements. So does both of them simultaneously justify, or any of them, combinations of them satisfy the case? So I'll read through the statement. For any robotic system, it is impossible to obtain the exact dynamic model of the system due to numerous factors. This demands the need of a motion controller. Is that true or false? First statement, is it true or false? It is impossible to obtain exact dynamic model of a system. So that seems to be a fairly straightforward statement. We don't really need any second guessing for that. For the second statement, the presence of external disturbance and the uncertainties in determining the parameters of a system calls for the design of a motion controller. That is also true, right? So if we derive a dynamic model, there is always uncertainties associated with the parameters. So in that regard, we cannot have an exact dynamic model or an exact representation of a dynamic model. So in that regard, that statement is also true. So from the following option, we have to select an option that says both statements 1 and 2 are true. So I guess it's option C, both statements 1 and 2 justify the need of a motion controller. That's also actually true. So yeah, option C is again true. Now, moving on to question 7. Which of the following statements are true for model-based controller? Right, model-based controller without any feedback terms. So the first statement, it's a pure feedback or sensing based on reactive scheme. That is obviously false, because it's only based on the mathematical model. It does not rely on feedback. And the second statement, it is easy to use, sluggish, and produce poor tracking performance. That is also false, because this statement is attributed to a model free or motion based scheme. And this is not attributed to the model based scheme. And the third option is they are comparatively efficient and simple to use than model free scheme. That is also true. This one is true. They are comparatively efficient because, as we have seen earlier with an example, models motion based are always sluggish. We have to wait until the error gets accumulated. But in a model based scheme, we know some information about the model. So in that regard, they are much more efficient and faster than model free schemes. And the fourth statement says, for the model-based scheme to work out, accurate model of the system should be available. That is a fairly straightforward statement. For a system that is reliant on model to work, the model itself will have to be accurate. So that's also true. So in that regard, statements 3 and 4 are correct. So option A, we have to choose option A because only options 3 and 4 are correct. That's for question 7. Moving on to question 8. In order for the inverse differential kinematic control law to work, which of the following conditions has to be guaranteed, must be guaranteed? Out of all the 6 options, which of the following options must be guaranteed? If anyone knows the answer, you can always let us know. So, in case of an inverse dynamic scheme, you essentially have mu, the kinematic equation is something like eta dot would be j of q multiplied by q dot. And this, for the controller to track a desired trajectory, q desired and q desired dot, or q desired of t and q desired dot of t, if the controller has to track this trajectory, what we have to do is we plug in these coordinates into this equation and find out the control input. So the control input q dot is nothing but j of q desired inverse eta desired dot of t, right? And for this control scheme to work, eta desired dot of t should not be 0, and the initial position, eta desired of t equal to 0 should be equal to the actual starting position, eta of t equal to 0. So these are the two conditions for the inverse differential kinematics to work. Right? So I think in the options, instead of eta, I've used mu. But which of these options conform to these two conditions? I think option A looks to be the correct one. Option A. Okay. If any further clarification is required, please let me know. Option A is indeed the correct answer. Now, moving on to question 9. This is a very similar question, but this time, instead of inverse kinematics, we deal with inverse dynamics law. So, given a desired trajectory, eta desired of t, eta desired dot of t, and eta desired double dot of t, what should be the because this inverse dynamics control scheme is an open loop control scheme. What should be the open loop control input tau? So from the inverse dynamics equation, we know that tau is nothing but m of q multiplied by q double dot plus n of q dot. So if you substitute this desired trajectory directly into this equation of motion, you will get the open loop control input. So that makes it m of q desired multiplied by q desired double dot plus n of q desired dot. And for this open loop control scheme to work, q desired double dot should not be 0, and the initial position q desired of t equal to 0 should be equal to the actual starting position, q of t equal to 0, and the initial desired velocity, q desired dot of at t equal to 0 should be the actual start velocity, q dot of t equal to 0. So now we have three conditions over here, out of which I believe the answer is to be option C. Yes, option C. Now, moving on to the second last question for this session. The question basically says, the controller of a robot manipulator is required to follow the second order error dynamics. We want the controller to follow the second order error dynamics. Q tilde double dot plus lambda 1 Q tilde dot plus lambda 2 Q tilde equal to 0, where Q tilde is the difference between the desired and actual position, and lambda 1 and lambda 2 are, greater than 0. If the dynamic equations of the robot are given as this one, what is the control input tau c to achieve this aerodynamics? What should be the control input so that the this robotic system can realize this aerodynamics? So as I was saying earlier, the benefit of this aerodynamics is that as t tend to infinity, q tilde of t tend to 0 and q tilde dot of t also tend to 0. Right? So from this aerodynamics, I am substituting, instead of q tilde double dot, I'm substituting q desired double dot minus q double dot plus lambda 1 q tilde dot plus lambda 2 q tilde equal to 0. And from this dynamics, I'll write this as over here as dynamics. So I'll label this as equation A, and from dynamics, I'm simply rearranging this dynamics equation of motion. So q double dot now would be tau minus n of q dot, the whole thing pre-multiplied by m of q inverse. I'll label this as equation B. So now substituting B in A, you would get q desired double dot minus m of q inverse tau minus n of q dot plus lambda 1 q tilde dot plus lambda 2 q tilde. This would be equal to 0. And from the above equation, the control input tau would look something like q desired double dot plus lambda 1 q tilde dot plus lambda 2 q tilde, the whole multiplied by m of q plus n of q tilde. This would be your controlling. This has to be a control input so that your system will follow this second order aerodynamics. So if you get your system to follow the second order aerodynamics, your position error will asymptotically tend to 0 and your velocity error will also asymptotically tend to 0. So I hope that is clear. In that regard, the correct option is option B over here. Right. So now moving on to the final question of today's session. Pick the odd one out of the following. So does anyone want to attempt this question? Odd one out? It's based on the classification of different kinds of controller. I'll give one more hint. You can classify the controllers as open loop or closed loop controllers. So if all the options can be classified as open loop and closed loop controllers, what will be the odd one out? Any answers? So the cascaded control, which is being taught in the lectures, this is a closed loop control. PID control is also a closed loop control because the P and I and D basically deals with the proportional and integral and derivative variation in the error itself, and error is nothing but the difference between the desired and actual variable. PD also similarly is a closed loop control scheme. Computer torque control, this is something what we have seen just above in the previous question. This is also a closed loop. Computed velocity kinematic control, that also we have discussed. This is also a closed loop. But inverse dynamics control is an open loop control. Right? We are simply plugging in the desired trajectory into the equation of motion. There is no feedback involved in it. So the odd one out from this set of 6 options is the inverse dynamics control. So similarly, inverse differential kinematic control is also open loop, but that is not in this option. All right. So the correct answer is option A. Yeah. So with that, we have come to the end of this session on motion control. If there are any questions, I can take it. Otherwise, we can wrap up this session. So are there any questions? Okay, so I hope there are no questions, so we can wrap up the session. Thank you all for joining. I am winding up the session. Thank you.
Thank you.
Thank you. Yeah.